You trust empty space more than you realize, not in any conscious way, not because you thought about it and decided it was trustworthy. You trust it the way you trust the silence between heartbeats, automatically, without checking. The gap between your hand and the wall before you reach for it. The darkness between stars when you look up on a clear night. The stillness inside a room when everything goes quiet and there is nothing left to hear. You do not look at those spaces and feel uncertain. You feel nothing at all, which is precisely the point. Empty space is the one thing in the universe that seems like it should not require an explanation. Matter is complicated. Light is strange. Black holes are extreme. But emptiness should be the easy part. Remove everything, and what remains should be simple. Should be obvious. Should be, by definition, nothing. Physics has spent the last 100 years discovering that this is wrong. Not slightly wrong. Not wrong in a technical way that only matters inside a laboratory. Wrong in a way that touches the expansion of the universe, the fate of everything that exists, and the deepest conflict between the two most successful theories science has ever produced. The thing we call empty space is not nothing. It has never been nothing. And when physics tries to explain what it actually is, the answer it returns is one of the most disturbing mismatches in the history of human knowledge. Tonight, we are not asking what fills the universe, we are asking something colder. What remains when you remove everything? And why does the answer break physics at its foundation? Get comfortable, and if this is your first time here, subscribe to Novarium, because tonight we are going into the quietest place in the universe, and the quiet is not empty. There is a room I keep coming back to in my mind when I think about this. Not a dramatic room, just an ordinary one. Late at night, after everyone has left. The furniture is gone. The objects are cleared away. The air is still. The lights are off and there is nothing moving anywhere. And there is this moment where the room feels like pure absence, where the space itself feels like the most complete silence you could find anywhere, like nothing could be more empty than this. I used to think that was close to what physics meant when it talked about empty space, a container with nothing in it, a stage with no actors, no props, no sound, just the stage itself, waiting, neutral, inert, perfectly, utterly nothing. That image is wrong. And the way it is wrong is what this entire video is about. Start with the oldest picture of space, the one that feels most natural, because it is the one built into everyday language and everyday intuition. In the physics that dominated thinking from the 1600s through the 1800s, space was essentially a container, a backdrop, an absolute and unchanging stage on which the events of the universe played out. Newton described a cosmos made of objects separated by distances. The objects moved. They had mass. They exerted gravitational pull on each other across the gaps between them. But space itself was not a participant in any of this. It was the room the furniture sat in. Passive, fixed, featureless. If you removed all the furniture, the room remained. Empty, yes. But still there. Perfectly inert. Perfectly silent. Asking nothing and offering nothing. This is a deeply satisfying picture because it matches experience so precisely. You can measure distances, you can describe locations, you can track motion through space and everything behaves as expected. Objects fall at the rates Newton predicted. Planets follow the orbits his equations described with extraordinary accuracy. The container model of space worked so well for so long that questioning it felt almost philosophical. Not really physics. Not really something worth worrying about in a serious scientific context. Then Einstein changed what space was. General relativity, published in 1915, did not simply add detail to Newton's picture. It replaced the picture entirely. In Einstein's framework, space is not a passive container. Space is an active participant. It bends, it stretches, it curves in response to the presence of mass and energy. What we experience as gravity is not a force reaching across distance in the Newtonian sense, some invisible hand pulling objects toward each other through empty nothing. It is the shape of space-time itself. A massive object like the Earth curves the geometry of the space-time around it, and other objects follow those curves the way a marble rolls along the inside of a curved bowl. The marble does not feel a force pulling it inward. It follows the shape of the surface it is moving along. Gravity is geometry. The curvature of space is the force. This is already a profound shift in what space means. But the part that matters most for what we are exploring tonight is what it implies about empty space specifically. If space can curve, stretch, and change its geometry in response to what is placed within it, then empty space is not inert. It has properties. It has structure. It can carry information about the curvature caused by nearby mass, even in regions where there is no mass at all. The gravitational field of the Earth extends into the space around it. That space is shaped by the Earth even where the Earth is not. The room is not passive. The room responds to what has been in it, and the room can grow. Edwin Hubble confirmed in 1929 that the universe is expanding. Distant galaxies are moving away from us, not because they are traveling through space in the ordinary sense, as objects moving across a fixed background, but because the space between us and them is stretching. The fabric is growing. The gap between here and there is not being crossed. It is increasing because the medium itself is enlarging. This was a shock, but it fit the equations. General relativity had actually predicted a dynamic universe before Hubble ever looked at the sky. Einstein had initially added a specific term to his equations to prevent the mathematics from implying expansion, because everyone at the time assumed the cosmos was static and eternal. When Hubble's observations arrived, Einstein removed that term. The universe was not static. It was expanding. The equations had known it before the observations confirmed it. The term Einstein added and then removed was called the cosmological constant, a small adjustment embedded in the geometry of his equations, a number he inserted to hold the universe still. When he took it out, he called it the greatest blunder of his career. He believed he had wasted an opportunity to predict one of the most important facts about the cosmos. But the story does not end there. Because blunders in physics sometimes turn out to be necessary after all. For decades after Hubble, the expanding universe was treated as a settled fact. Space was growing outward. Gravity was pulling back. The interesting scientific question was simply how much gravity mattered. Would the expansion slow gradually and continue forever? Would gravity eventually win and pull everything back together into a final collapse? Astronomers in the late 1990s set out to measure the deceleration rate with precision. They used a particular kind of exploding star, a Type 1, a supernova, as a standard measuring tool. These supernovae detonate at roughly the same intrinsic brightness. So by measuring how dim they appear from Earth, you can calculate how far away they are. Dying stars as rulers, stretched across the cosmos. Two independent teams, one led by Saul Perlmutter at Berkeley, one by Brian Schmidt and Adam Rees working separately on the other side of the world, pointed these rulers at distant supernovae and expected to measure something boring. A cleaner number on a question everyone thought was nearly closed. What they found instead stopped both teams. The supernovae were dimmer than they should have been, not by a tiny amount. Consistently, across many independent measurements, at distances suggesting they were farther away than a decelerating universe would place them. The expansion was not slowing, it was speeding up. The universe was not just growing, it was growing faster and faster over time, accelerating outward at an increasing rate. Something was pushing. Something was driving this acceleration harder than the collective gravity of every visible object in the observable universe was resisting it. Something associated with space itself, pervasive, persistent, not concentrated in any object or region, but spread everywhere that space exists. We called it dark energy. And that name deserves a moment of honest attention, because the name is not a description. It is a label on a blank. It does not tell you what the thing is. It does not describe a mechanism or point toward a source. It names the effect and admits ignorance about the cause. Dark energy accounts for roughly 68% of the total energy content of the observable universe. The entire visible cosmos, every star and planet and gas cloud and galaxy you have ever seen in any photograph taken by any telescope, accounts for approximately 5%. Dark matter accounts for most of the rest. And the dominant ingredient of the universe, the component that is actively determining the fate of everything that exists, has no agreed-upon explanation more than 2 decades after its discovery. Perlmutter, Schmidt, and Rees won the Nobel Prize in 2011. The prize recognized what they found. It had nothing useful to say about why what they found has no explanation. Now here is where Einstein's discarded mistake becomes necessary. When physicists looked at the mathematics of accelerating expansion, they found that the term Einstein had added and then removed, the cosmological constant, was precisely the kind of mathematical structure needed to describe what was happening. A constant energy density associated with space itself, not with matter distributed through space, not with radiation crossing space, with the space. The cosmological constant behaves, within the geometry of general relativity, like an energy that belongs to empty space, everywhere and always. As space expands, the density of ordinary matter decreases. Atoms spread out, radiation dilutes. But the cosmological constant does not behave that way. Its energy density remains fixed even as space grows. More space means more total energy of this kind, because the density per unit volume stays constant while the volume increases. This is already a strange property. But the cosmological constant is not just a mathematical curiosity. It is the number that decides how the universe ends. If the constant remains exactly as it appears to be now, the expansion continues accelerating indefinitely. Galaxies already distant will recede past the point where their light can ever reach us. The observable universe shrinks, not because space contracts, but because accelerating expansion carries more and more of it beyond our cosmological horizon. Stars burn out one by one across trillions of years. The last ones fade slowly. What remains is a cold, extraordinarily dilute, vast expanse dominated by the energy of the vacuum itself. No stars, no light, no warmth. A universe that does not end dramatically, but loses the thread of itself slowly, becoming quieter and more diffuse until there is nothing left that deserves to be called structure. Physicists sometimes call this the heat death, or the big freeze. The universe does not end. It only forgets. If the energy grows instead of holding constant, everything changes. The push that currently separates galaxy clusters would eventually begin separating individual galaxies. Then solar systems, then planets, then the molecules of matter, then the atoms themselves. Robert Caldwell at Dartmouth calculated in 2003 that under certain models of growing dark energy, this process could complete in a finite span of time. The fabric of space-time itself comes apart. Not a slow dissolution, but a progressive tearing of everything that coheres. The Big Rip. Everything that exists, disassembled piece by piece by the expansion of the space between its parts. If the energy weakens over time, gravity reasserts dominance. Expansion slows, stops, reverses. Everything that has been flying apart for 13.8 billion years begins falling back inward. The compression heats everything. The final state mirrors the initial one, the Big Crunch, a reversal of the beginning, with everything that ever existed compressed into a volume smaller than anything we can meaningfully describe. 3 futures, 3 completely different endings to every story that exists. And the number that decides which one is real is a number that physics cannot currently explain from first principles. This is not a gap at the fringes of the map, it is a gap at the center. And to understand why, you have to move from cosmology to quantum mechanics, from the very large to the very small. Because there is a second way that physics approaches the energy of empty space, and it comes from a completely different direction, through a completely different framework, using completely different mathematics. And when the two approaches meet, the result is what some physicists have quietly described as the worst prediction in the history of science. Quantum field theory is the framework that describes particles and forces at the scale of atoms and below. It is extraordinarily successful. The predictions it makes for certain measurable quantities agree with experiment to more decimal places than any other theory in any scientific field. Its description of how electrons interact with light matches experimental measurement to roughly 1 part in a trillion. This is not a tentative or approximate framework. It is the most precisely tested description of nature that human beings have ever produced. And one of its foundational claims, one that emerges directly from its core mathematical structure, is that empty space is not nothing. Here is the core of that idea. In quantum field theory, the universe is not made of particles sitting in an otherwise empty background. It is made of fields. Fields that exist everywhere, always, filling all of space continuously and completely. Particles are not tiny objects placed into an empty setting. They are disturbances in these fields. Ripples. Excitations. An electron is not a small bead floating in a void. It is an excitation of the electron field, a particular kind of disturbance in something that is already present everywhere. A photon is an excitation of the electromagnetic field. A quark is an excitation of the relevant quark field. Every known particle corresponds to a field that pervades all of space at every moment, regardless of whether there are any particles present at all. That last part is the one that carries everything. The fields do not disappear when there are no particles. The fields are always there. They are the substrate, the foundation. Particles are what happens when you disturb the substrate. The field is primary. The particle is secondary. So when you imagine removing every particle from a region of space, removing every atom and every photon and every dust grain and every neutrino and every other known particle, you are not removing the fields. The fields remain. They have to remain. They are not optional objects sitting in space. They are more fundamental than that. And this is exactly what physics means when it uses the word vacuum. Not nothing. The lowest possible energy state of all the quantum fields that exist, the quietest configuration the universe can achieve while still obeying the rules of quantum mechanics. And here is the crucial point. The lowest possible energy state is not the same as zero activity. Quantum mechanics contains a constraint called the uncertainty principle. In its most familiar form, it says you cannot simultaneously know the exact position and exact momentum of a particle with perfect precision. The more sharply you pin down one, the more uncertain the other becomes. But the uncertainty principle applies more broadly than just position and momentum. It applies to pairs of quantities that are related in the appropriate mathematical way, including the value of a quantum field and the rate at which that value is changing. This means a quantum field cannot simply sit at exactly zero value with exactly zero rate of change simultaneously. That would require perfect knowledge of both quantities at once, which the uncertainty principle forbids. The field must fluctuate, even in the vacuum state, even at its absolute lowest energy. The field trembles because the laws of quantum mechanics do not permit the perfect stillness that classical physics would allow. The vacuum is not a lake at rest. It is a lake at the lowest temperature physically possible, and even there, quantum mechanics requires that it continues to ripple. Not because something disturbs it from outside, because the rules of the theory do not permit it to be still. This is not a metaphor and not hand-waving. It is a direct mathematical consequence of applying quantum mechanics to fields. The vacuum state of a quantum field carries irreducible activity built into it by the structure of the theory itself. The popular description of this activity involves what are often called virtual particles, pairs of particles briefly flickering into existence and then annihilating, too short-lived to be directly observed. This image is not entirely wrong, but it is a simplification. The underlying reality is better described as quantum fields with unavoidable uncertainty in their values. The field language is more accurate. The particle language is a useful metaphor that can be taken too literally if you are not careful. The actual content is this: the vacuum has activity, the vacuum has structure, and the vacuum appears to have energy. Every quantum field in its lowest energy state carries what physicists call 0-point energy. This is the energy that remains in the ground state, the energy you cannot remove no matter how thoroughly you drain the system. It is not zero. It has a value. And if you add up the 0-point energy contributions from every quantum field that physics currently describes, the total is a specific, calculable number. A number with physical significance, a number that should correspond to something observable in the universe. Before reaching the crisis at the center of all of this, it is worth pausing on a piece of physical evidence that makes the vacuum energy real in a concrete and measurable way. Not a theoretical inference, an actual laboratory result. A real force produced by the structure of empty space, measured with instruments, confirmed with precision, and impossible to explain if empty space were actually empty. Imagine two flat metal plates placed very close together. Extremely close, separated by a distance of only a few micrometers. The plates are electrically uncharged. There is no air between them, no fluid, no visible matter of any kind filling the gap, nothing pushing them or pulling them from the outside. In classical physics, nothing should happen. The gap is empty. Empty means no force. That is the entire classical prediction. In 1948, a Dutch physicist named Hendrik Casimir calculated that something would happen. He predicted that the vacuum itself would push the plates together, not because of any material substance between them, but because of the structure of the vacuum fluctuations in the gap. Outside the plates, the electromagnetic field can fluctuate in any mode, any wavelength, any frequency. Inside the narrow gap between the plates, only certain modes fit. The separation of the plates acts as a boundary condition that restricts which fluctuations are permitted in the enclosed space. Fewer modes are available between the plates than outside them. This difference in the vacuum structure on either side of the plates creates a pressure imbalance. The outside pushes harder than the inside. The plates experience a net force drawing them together, not because of anything between them, because of how empty space is structured differently on each side of them. Casimir's prediction was confirmed experimentally, first in 1958, then with increasing precision in later decades. In 1997, Steve Lamoureux at Yale measured the Casimir force with an accuracy of around 5%, a result that was itself later refined further by other groups. The force is real, it is reproducible, it is tiny, but it is measurable, and it behaves exactly as the theory predicts. Two metal plates in a vacuum, nothing between them that any classical picture of empty space would acknowledge, pulled toward each other by the arrangement of the vacuum on either side. This is the vacuum made physical. This is the evidence that the 0-point energy of quantum fields is not just a mathematical artifact that cancels out when you do the calculation carefully. It has real, measurable, physical consequences that you can measure in a laboratory. Empty space has structure. That structure has effects. The effects can be measured. The measurements match the theory. Now here is where the wound opens. If the vacuum has energy, and if that energy can be calculated from the quantum fields that physics describes, and if the Casimir effect confirms that at least some version of this energy is physically real, then the calculation should give you a number that corresponds to something observable at cosmological scales. The cosmological constant that astronomers measure, the one that drives the accelerating expansion of the universe, should match the vacuum energy that quantum field theory predicts. Both of them are attempting to describe the energy of empty space. Both of them are grounded in well-tested physics. They should agree with each other. They do not agree. Depending on how the calculation is constructed and where you set the cutoff for contributions from different fields, the vacuum energy predicted by quantum field theory exceeds the cosmological constant, measured by cosmology by a factor somewhere between 10 to the 60th and 10 to the 120th power. The range of the discrepancy depends on theoretical assumptions about where the calculation loses validity, which is itself an unresolved question. But even the most conservative, reasonable version of the mismatch is staggering. And the version most frequently cited, using the Planck scale as the natural energy cutoff, because that is where quantum gravity effects are expected to become important, gives a discrepancy of roughly 10 to the 120th, one followed by 120 zeros. Sit with that for a moment. This is not a rounding error. It is not a missing decimal place. It is not the kind of gap you close by recalibrating an instrument or being more careful about a calculation. The total number of atoms in the observable universe is approximately 10 to the 80 power. The discrepancy between the quantum field theory prediction for vacuum energy and the cosmologically observed value is larger than the total number of atoms in everything you can see, by 40 orders of magnitude. The prediction does not just miss, it misses by more than the universe contains. The most successful theory of the very small and the most successful theory of the very large are both, in their respective domains, extraordinarily reliable. Both are trusted with technology and human lives. And when you point them at the same thing, at the quiet energy of empty space, and ask them what they find, the answers they return are not even in the same neighborhood of values. They are not on the same map. I remember the moment I first actually tried to feel what this number means. Not just saw it written in a textbook with a dismissive footnote, but tried to understand it as a statement about two trusted frameworks contradicting each other. And it does not feel like a gap in knowledge. It feels like something structural. Like finding that two instruments you have relied on without question for a century are producing readings that differ by more than everything you can observe in any direction. And not knowing whether the problem is the instruments, or the thing they are trying to measure, or something about the relationship between measurement and reality itself. This is called the cosmological constant problem. It is sometimes described as the worst prediction in the history of physics, but that framing slightly misses what makes it genuinely disturbing. Wrong predictions happen. Physics corrects them and moves forward. The cosmological constant problem is sharper than a simple wrong prediction, and it has three distinct parts that together make it feel less like a solvable mistake and more like a structural crack in the foundation. The first part: why is the vacuum energy not enormous? If quantum field theory is correct about the existence of vacuum fluctuations, and the Casimir effect provides real evidence that it is at least partially correct, then the vacuum should carry a huge amount of energy, an amount that is enormous by any cosmological standard. But the universe we observe is not expanding at a rate consistent with an enormous vacuum energy density. Something must be cancelling most of the predicted energy before it contributes to the expansion. What is doing the cancelling, and why does it cancel with such precision, and why does it not cancel completely? Physicists have explored various mechanisms for this cancellation. Supersymmetry was among the most appealing candidates for decades. If every known particle has a supersymmetric partner with exactly the right properties, their contributions to the vacuum energy can cancel each other in a way that leaves a much smaller residual. This was a beautiful idea. The Large Hadron Collider has searched extensively for supersymmetric particles across multiple runs with billions of collisions. Not one supersymmetric particle has been found. Supersymmetry, if it exists in nature, is not present in the simple form that would make this cancellation work cleanly. Even if some cancellation mechanism exists and operates, it would have to be extraordinarily precise. The individual contributions to vacuum energy from different quantum fields are each enormous. For them to cancel down to the tiny observed value, the cancellation would have to be accurate to one part in roughly 10 to the 120th. That precision has no natural explanation in current physics. It is not protected by any known symmetry. It is not required by any known principle. It is simply a fact about the universe that physics currently has no account for. The second part: why is the vacuum energy not exactly zero? This seems like the same question, but it is meaningfully different. If some symmetry or deep principle drove the vacuum energy to exactly zero, that would be one kind of answer. Strange, perhaps, but at least it would be clean. But the observed value is not zero. It is small, but it is positive. And it is actively driving the accelerated expansion of the universe right now. A value of exactly zero would have a certain logical cleanliness to it. The observed tiny non-zero positive value is protected by no known symmetry, predicted by no known mechanism, and sits where it sits for reasons that physics cannot currently articulate. The third part is the one that underlies the other two and makes the whole problem feel existential rather than merely technical. The observed value of the cosmological constant sits in a range that permits the existence of structures like galaxies, stars, planets, and observers. Physicists have calculated what would happen under different values. If the vacuum energy density were significantly larger than observed, the accelerating expansion it drives would have been too rapid in the early universe for gravity to pull matter together into galaxies. The density fluctuations that seeded all the structure we see would have been dispersed before they could collapse. Galaxies would never have formed. Stars would never have ignited. The universe would have expanded into a smooth, featureless, rapidly thinning gas. If the vacuum energy was strongly negative rather than positive, the story would end differently but just as abruptly. The universe would have recollapsed long before the billions of years needed for stars to form, burn through multiple generations, scatter heavy elements into the interstellar medium, and provide the conditions for planetary chemistry. Everything would have been compressed back into oblivion in a fraction of the current age of the cosmos. The observed value sits in a narrow band. Not the only band that would permit something, but a band that is genuinely small compared to the full range of possible values that the underlying physics seems to allow. And nothing in current physics explains why the value is in that band. No derivation selects it. No principle points to it. It is simply where it is, and everything we know depends on it being there. This is the fine-tuning at the heart of the cosmological constant problem. It is important to be precise about what fine-tuning means and does not mean here. It is not a claim about design. It is not a philosophical or theological argument wearing scientific clothing. It is an observation about the relationship between a physical parameter and the structures that exist. The parameter has a value. The value permits structures. The theory that describes the parameter cannot explain the value. That is the complete statement. Everything else is interpretation. Some physicists argue that the answer lies in the existence of many universes. If there is an enormous landscape of possible universes, each with a different value of the cosmological constant drawn from the range the underlying theory allows, then we should not be surprised to find ourselves in one where the value is compatible with our existence. We could only observe a universe that permits observers. The fact that our universe has the right value is then no more mysterious than the fact that we live on a planet with liquid water. Of course we do. We could only live somewhere that supports us. This reasoning is associated with the anthropic principle in the context of the vacuum energy problem. Whether this constitutes a genuine explanation or a sophisticated avoidance of explanation is a question the physics community has not resolved. An argument that explains all possible observations by pointing out that we can only observe observations compatible with our existence is extremely difficult to falsify in the conventional scientific sense. It dissolves the puzzle by making all values of the parameter seem equally plausible in advance, which is either a solution or a category error depending on your view of what physics is supposed to do. The debate continues. What the field has agreed on is that the cosmological constant problem is real, unsolved, and sits at the intersection of the two frameworks that most need to be unified. Stay with the quantum vacuum a little longer, because there is more here than the energy problem alone. The vacuum is not simply energetic in a way that creates accounting difficulties. It is structured in ways that determine what matter actually is. Consider the Higgs field. The Higgs field is a quantum field that pervades all of space like the others. It is always present everywhere. But unlike most quantum fields, which have their lowest energy state at a field value of 0, the Higgs field has its lowest energy configuration at a specific non-zero value. Even in completely empty space, the Higgs field is not flat. It sits at a particular background value that is intrinsic to the vacuum itself. This is called the vacuum expectation value of the Higgs field. This matters because particles acquire their masses through their interaction with this background field. As a particle moves through space, it interacts with the Higgs field that is everywhere in the vacuum. The strength of this interaction determines what we call the particle's mass. A particle that couples strongly to the Higgs background acquires a large mass. One that couples weakly acquires a small mass. One that does not couple at all, like the photon, remains massless. The mass of every massive particle in the universe is not a fixed, internal property of a particle sitting alone in emptiness. It is a property of how the particle relates to the vacuum it moves through. The vacuum is not passive. It is setting the parameters for what matter is allowed to be. You are not moving through nothing. You are moving through a structured background whose field configuration determines the properties of every atom you are made of. The space around you, the silence in the room, the gap between objects, carries background field values that shape the fundamental character of matter itself. Remove the Higgs vacuum expectation value, and particles lose their masses. The chemistry of atoms becomes impossible. Nuclei cannot form. The universe becomes an undifferentiated plasma of massless particles moving at the speed of light. The emptiness around you is not neutral. It has settings. Those settings are not optional. They are what makes you possible. There is a further implication of this picture that deserves careful treatment. If the vacuum is a state, a specific configuration of quantum fields with particular properties and particular energies, then it is worth asking whether our current vacuum state is the only possible configuration, whether it is the absolute lowest energy state, whether there might be other configurations, lower in energy, that the universe has not transitioned to. This is the question of vacuum stability. Our current vacuum may be in what physicists call a metastable state, a configuration that is locally stable but not the absolute minimum energy. Think of a ball resting in a shallow bowl that is itself partway up a larger hill. The ball is not rolling. It appears stable, but if it received a sufficient push, or if quantum tunneling allowed it to pass through the barrier spontaneously, it could roll down to a deeper bowl further down the slope. If our vacuum were metastable in this sense, a transition to a lower energy configuration would be physically possible. Such a transition would not be gradual. It would expand outward as a bubble of new vacuum, growing at the speed of light in all directions from wherever the transition began. Inside the bubble, the vacuum expectation values of fields would be different. The masses of particles would change. The strengths of forces would change. The chemistry of matter would become unrecognizable or impossible. The bubble would carry no warning signal ahead of it. No light could outrun it. There would be no observation of its approach. It would simply arrive. I want to be precise about what physics actually says here. This is a genuine theoretical possibility, not a prediction of imminent catastrophe. We do not know with certainty whether our vacuum is metastable. The calculation depends on the detailed structure of the potential energy landscape of quantum fields at high energies, which involves assumptions that go beyond currently confirmed physics. Some theoretical work, particularly related to the measured value of the Higgs mass and its implications for the shape of the Higgs potential at high energies, suggests our vacuum may sit near the boundary between stability and metastability. But this is a tentative theoretical inference, not a firm conclusion. Different groups doing the calculation with different assumptions get different answers about exactly where on the stability boundary we sit. What the possibility illustrates, regardless of whether it will ever occur, is something important about the nature of the vacuum itself. The vacuum is not a neutral backdrop. It is a condition, a phase, a state the universe currently occupies. Empty space is not the absence of properties. It is a specific configuration of properties. Configurations can, in principle, change. If the configuration changed, the empty space of the new vacuum would not be the same empty space as our current one. The rules of physics inside it would be different. What we call emptiness is a particular state of the fields, not a universal fact about absence. This is already an enormous distance from the intuition that empty space means simple nothing. But there is one more step, and it may be the most philosophically vertiginous. What would it mean for space to be truly absent? Not empty. Absent. No geometry, no distance, no coordinates, no location, no here and no there. This is different from empty space in an important way. Empty space is a region with no particles or radiation. It still has geometry. It still has distance. You can still point at a location within it and say, that location is real. No space means none of that applies, no location to point at, no distance to measure, no structure within which an event could have a position, nothing that would allow you to even formulate the question of what is inside it. Because inside requires the concept of a boundary, and a boundary requires geometry. And geometry is exactly what is absent. Physics does not handle this well. Not because physics is inadequate for the question, but because the question may not be a physical question in the usual sense. To describe anything in physics, you need a framework. Laws, equations, boundary conditions, a notion of state. Even to discuss the beginning of the universe, or the possibility of something arising from nothing, requires specifying what kind of nothing you mean. A quantum vacuum with fluctuations is not nothing in any absolute sense. A space-time with no matter is not nothing. Even the most stripped-down version of nothingness that any physical formalism can represent still carries the structure of the formalism itself. The moment physics can say anything about a thing, that thing is already something. The framework needed to describe it gives it properties. A state of no fields, no laws, no space, no time, and no geometry is not a state that any physical equation can represent, because representing a state requires a framework, and the framework would constitute the something that the nothing is supposed to exclude. True absolute nothingness falls outside the map entirely. And the disturbing implication is that this boundary, the place where physics goes silent, may not be at some extreme distance or extreme energy where we would expect the map to run out. It may be at the most fundamental question of all. Why is there anything? A question that every physical framework ever constructed takes for granted by assuming something is already present to describe. None of this makes the world less solid. The atoms hold. The stars shine. The equations predict, and the predictions land with extraordinary precision. This is important to say plainly, because the story of the vacuum is sometimes told in a way that makes reality seem fragile or unstable. It is not. The physics is solid where it is solid. The gap is not in the surface of things. The gap is underneath, in the foundation. And the foundation matters because of what it determines about the very long future. As the universe expands under a stable cosmological constant, ordinary matter dilutes. The density of atoms decreases as space grows. Galaxies spread apart. Gas that could form new stars thins out across ever larger volumes. The rate of star formation slows and eventually stops. Existing stars burn through their fuel and die. Over timescales vastly longer than the current age of the universe, the last stellar embers fade. But vacuum energy, if it behaves as the cosmological constant appears to behave, does not dilute. Its density stays constant as space expands. More space means more total vacuum energy. The vacuum does not thin as everything else does. So the universe is moving toward a state where empty space wins. Not because there is nothing, because what remains is the energy of the vacuum itself, spread across an increasingly vast and cold expanse, governing the geometry of a cosmos that has long since exhausted its visible contents. The ultimate future of everything that exists, if current physics is correct, is a universe dominated by what we used to call nothing. A universe in which the most important ingredient is the energy of the silence itself. The dark between the stars, the stillness inside a room at midnight, the space between your hand and whatever surface is nearest to it right now, these have never been nothing. They have always been fields in their lowest state, trembling because quantum mechanics does not permit stillness. They have always carried the cosmological constant, the small and stubborn and unexplained energy that is pushing everything apart and deciding the shape of the end. They have always been structured by the Higgs field's background value, which is what gives your atoms the masses they have. The absence was never empty. It was the vacuum. And the vacuum has properties, energy, pressure, structure, and consequences that extend to the largest scales in the observable cosmos. The problem is not that physicists failed to notice this. The problem is that they noticed and then tried to calculate it. and the calculation returned a number that does not match. The two most successful frameworks ever built for understanding reality both agree that empty space has energy. They disagree on how much by a factor that cannot be written in ordinary notation without resorting to exponents of exponents. And the actual measured value sits between the two predictions in a place that has no theoretical home. Physicists have known about this problem for decades. It is not a new puzzle that emerged from a recent surprise observation. The cosmological constant problem was understood to be a serious issue long before the accelerated expansion was confirmed in 1998. The discovery of the acceleration made it more acute because now the cosmological constant was not just a theoretical embarrassment. It was a measurable quantity with a specific value that demanded explanation. The theory of the very small predicts a value 10 to the 120th times too large. The theory of the very large observes the actual value. Both theories are correct in their domains, and the number they cannot reconcile is the number that determines the fate of everything. This is where the deepest tension in modern physics lives, not in some exotic corner of the subject, not in the study of phenomena so rare or distant that most physicists can set them aside. It lives in the most ordinary feature of reality, in the quiet, in the space between things. General relativity describes the large, the curvature of space-time, the behavior of gravity across cosmic distances, the bending of light around massive objects, the expansion of the universe. Its predictions are tested by gravitational wave detectors, by the precision timing of pulsars, by the orbit of Mercury, by the deflection of starlight around the sun. Every test has confirmed it with extraordinary precision. It is one of the most thoroughly verified physical theories ever developed. Quantum field theory describes the small, the interactions of particles and forces at atomic and subatomic scales. Its predictions have been confirmed to levels of precision that exceed everything else in science. Both frameworks are right. Both are trusted completely in their respective domains, and they cannot be combined into a single consistent picture of reality. General relativity describes space-time as smooth, continuous, and deterministic. A classical geometry that curves and stretches, but does not fluctuate in the quantum sense. Quantum mechanics requires uncertainty. It requires fluctuations. It requires a fundamentally probabilistic description of any system at small enough scales, including, in principle, space-time itself. At the scales relevant to everyday physics and even to most laboratory experiments, the domains of these two theories do not overlap and the tension does not produce observable contradictions. But at the Planck scale, where lengths reach 10 to the negative 35 meters and time intervals reach 10 to the negative 43 seconds, both theories become simultaneously relevant. And at that scale, they contradict each other in ways that no mathematical technique has yet resolved. The vacuum energy problem lives precisely in this contradiction. Quantum field theory computes the vacuum energy by summing contributions from fluctuations up to some energy cutoff. The most natural and physically motivated cutoff is the Planck scale, the point where quantum gravity effects become unavoidable and where the smooth spacetime assumed by the calculation is no longer a reliable picture. But a complete theory of quantum gravity, one that would tell you what actually happens at the Planck scale and allow you to compute the vacuum energy correctly within a unified framework, does not yet exist. The calculation that produces the devastating mismatch uses quantum field theory to predict the vacuum energy and then compares the prediction to what cosmology observes through general relativity. But it does so in a regime where neither theory is on fully solid ground. The mismatch may be telling us that we are using the wrong tools, that the frameworks themselves need to be replaced by something deeper, something that has not yet been found. Physicists have been searching for that deeper framework for most of a century. Loop quantum gravity proposes that space-time is not smooth and continuous at small scales, but is instead built from discrete units, a kind of quantum granularity to the fabric of space. String theory proposes that the fundamental objects are not point particles, but extended one-dimensional objects, whose different vibrational modes correspond to different particles and forces. Causal set theory proposes that space-time is built from a discrete collection of causally related events rather than from a continuous manifold. Each approach is an attempt to find the framework that both general relativity and quantum mechanics are approximations of. None has yet produced a complete and experimentally testable description of physics at the Planck scale. None has resolved the cosmological constant problem from first principles. The gap remains open. What we have at the present moment is an unusual situation. Both primary tools of modern physics are verified beyond reasonable doubt in their respective domains. And when pointed at the vacuum, the simplest and most apparently featureless region of reality, they return answers that cannot be reconciled with each other or with what the universe actually shows us. Nothing should have been the easy part. The silence should have been where the equations agreed most cleanly. Instead, the silence is where they disagree most catastrophically. And this disagreement is not hidden in some abstract mathematical space that has no connection to observable reality. It is about the energy of empty space, the same empty space that fills your room, the same empty space between the stars you look at on a clear night, the same empty space inside every atom in your body. The equations that describe the world you live in cannot agree on what that space is. They can measure its effects. They can track the acceleration it drives across the observable universe. They can measure the tiny force it exerts between two metal plates. But they cannot explain the value of the energy it carries, and the failure is not subtle. It is by the largest margin of error that exists anywhere in science. I think about this sometimes in the quiet hours of the night, when everything around me is still and the room has that feeling of pure absence, when nothing is moving and nothing is making any sound, and the space between objects feels as empty and uncomplicated as anything can feel. And I try to hold both things at once. The stillness is real. The room is genuinely quiet. And underneath that quiet, in the fields that fill every cubic centimeter of that apparently empty air, there is a structure that physics cannot fully account for. An energy that the equations can measure in its effects, but cannot explain in its magnitude. A trembling that quantum mechanics requires and that leaves its mark on metal plates, drawn together by forces that empty space should not be able to exert. The vacuum is not the absence of reality. It appears to be one of reality's deepest layers. The layer that persists when everything removable has been removed. The one that does not vanish when the particles are gone because it is not made of particles. It is the state of the fields, the condition of the quantum substrate, the minimum configuration that the laws of physics allow. And that minimum configuration is not well understood. The best calculation we can make overshoots the observed value by more than any number in astronomy. The two frameworks that describe the rest of reality with extraordinary success cannot be reconciled in this domain. The mechanism that sets the vacuum energy to its observed value, tiny but non-zero, small enough to allow galaxies and stars and chemistry and everything that followed, is not known. Physicists do not have a leading candidate for the resolution. They have proposals and conjectures and approaches that each face serious obstacles. The problem has been open and clearly articulated for more than 2 decades since the acceleration was discovered, and in that time it has not narrowed in any fundamental way. What has happened in that time is that the certainty that the problem is real has grown. The measurements of the cosmological constant have become more precise. The absence of supersymmetric particles at the energies the LHC can reach has closed off some of the most appealing theoretical exits. The failure of string theory's landscape to produce a unique prediction for the vacuum energy has made the problem feel less like a technical challenge awaiting a clever solution and more like a fundamental indicator that something important is missing from the picture. Not a detail, a structural element. Something about the relationship between quantum theory and gravity that physics has not yet found the right language to describe. The world still works. This is the thing to hold on to when the implications of the vacuum problem start to feel vertiginous. The floor holds, the atoms bind, the chemistry runs, the sun rises on the schedule that physics predicts. None of what we have explored tonight destabilizes the ordinary workings of reality. The equations that govern your experience are reliable. The gap is not in the machinery. It is in the explanation of the machinery. But the explanation matters, not because the world will stop working without it. It will not. But because the cosmological constant, the energy of empty space, is not a detail of the universe, it is the ingredient that is winning. As the universe ages and ordinary matter dilutes, and stars die and galaxies drift apart and the cosmos becomes quieter and colder and emptier, the one thing that does not thin out is the vacuum. The one thing that does not fade is the energy of the space itself. The future belongs to the vacuum, and physics cannot tell us what the vacuum fundamentally is. Maybe empty space was never the absence of the universe. Maybe it was always the universe showing us its lowest layer, the one beneath matter and radiation and light, the one that the fields settle into when everything else has been taken away, the one that trembles with unavoidable quantum activity even at its quietest, the one that carries an energy whose value shapes the entire history and future of the cosmos, and whose origin remains one of the deepest unsolved problems in physics. We thought nothing would be simple. We thought emptiness would be the one thing that required no explanation. Physics found that nothing has structure, that it has energy and pressure and a vacuum expectation value, and a cosmological constant and a Casimir force and a fate-determining number that the two best theories in science cannot agree on. Physics found that the quietest place in the universe is where the equations fail most completely and most quietly. And tonight, when the room goes dark and the space between objects fades into silence, remember this: the darkness is not empty. It only looks that way from the surface. Underneath, the fields are still there, still in their lowest state, still trembling, still carrying the number that decides how everything ends. And physics is still searching, carefully and without certainty, for the reason that number is what it is. The search is ongoing. The silence is not empty. And the most ordinary absence in the universe may be the place where the deepest question still lives, unanswered, in the dark.